Since this is a chemical engineering discussion, I'm going to give what I believe is a chemical engineering perspective on this theme. And it's, of course, a very important theme, sustainability. Um, and there's a long history of the role of chemical engineers in building up our standard of living and the quality of life and so on. Now we have a much more sophisticated and nuanced strategy to keep that and improve that quality of life into the future, well into the future. And that's what sustainability is all about. The other thing I like about this opportunity to have this discussion this morning to a community of chemical engineers is that we all have this common background, namely our undergraduate class in thermodynamics. So if you kind of step back and look at the big picture, and if you just talk about life in general, not even human life, but just life, whether it's plants or animals, life represents a localized optimum from an entropy perspective in terms of order in a background or environment that is relatively disordered, right? So going back to your class in thermodynamics and the three laws of thermodynamics, the first law, the second law, and third law, one of the concepts we learned was entropy. So if you think about life in general, what does it mean when a predator eats a prey to maintain its life? Obviously, it's one particular point in space-time, namely the predator's life, that maintains its order by increasing the disorder in its environment, right? So obviously, the prey that was consumed, it is no longer the optimum in entropy because now its proteins and nutrients are its molecules are literally disintegrated and reassembled to form the molecules in the predator, okay? And that's what life is, okay? And when plants do photosynthesis, it's taking energy from sunlight, it's taking nitrogen from the environment, it's taking water from the environment, it's taking carbon dioxide from the environment, it's taking all sorts of relatively less ordered molecules from the environment, and it's assembling it into a highly ordered structure, which is the fabric of the plant. Okay, so if you kind of step back and look at the big picture from a thermodynamics perspective, that is what life is about. Okay, so then we ask ourselves, in the early days of civilization, including the Industrial Revolution, and maybe up to the first 3/4 of the previous century. So the first 3/4 of the previous of the 20th century, we built up our quality of life, especially in the wealthy nations like the United States, by taking a shortcut. If you think about burning fossil fuels as energy sources, and using fossil fuels as the feedstock for our petrochemicals and much of our modern society. That includes things like plastics, as well as other high performance materials and so on. And chemical engineers have, of course, historically been the field that has been instrumental in creating all this infrastructure that makes modern life possible. So what fossil fuels represents, and if you step back and instead of thinking of it from a morality perspective of whether it's good or bad, but just think of it from a perspective of thermodynamics, what depletable resources represents is the vast accumulation of an entropic optimum over literally millions of years. And then we've been smart enough and bright enough to figure out how to exploit that to further our own entropic aims. Okay, so we gain an entropic advantage by creating disorder. So when you burn fossil fuels to create energy for ourselves, or you use the fossil resources as feedstock for our modern economy. Basically, we're just taking all this stored optimum in entropy and using that for our own entropic purposes, okay? So that's what thermodynamics teaches us. And the reason why this perspective is important is there's a reason why we did this, because it is a shortcut, okay? It is the fastest way to gain entropic advantage for ourselves. Of course, in the long run, it's not a good strategy because as a depletable resource, it's going to run out. But in the short term, it is obviously a superior strategy because there's so much of it accumulated that if you try to use alternate strategies, it's not going to be as effective, right? So if you think of it from a purely competitive perspective of tribal rivalries or national rivalries or competitive rivalries between companies, unless there's a broad, almost societal, humanity-wide agreement that we're not going to do this, there will always be a strong incentive for some subset of humanity to take the shortcut, because in the short term, it's going to beat out and win, okay? And again, for chemical engineers, this is a relatively easy calculation. It's one of the first things you'll learn in your sophomore chemical engineering class, mass and energy balance course. At Purdue, this would be CHE 205. Every chemical engineering program has a similar course like that at the beginning in the sophomore year. And what you learn in that class is that the energy density, but really it's, in some sense, it's the density of the entropic optimization, is so high in these non-renewable resources that when you look at alternate strategies that point to a sustainable future, the density is simply not competitive, okay? Now, part of the challenge for the chemical engineering community is to share our technological insights in an honest and transparent manner so that we give the rest of the society honest and transparent advice. And because what you don't want is to give technologically inferior solution, either from ignorance or purely driven by ideological goals. Now, I'd like to give a simple analogy. If you're stranded in the middle of the ocean on a tiny boat, and there's no way to move the boat, and you're there by yourself, you're marooned, you're stranded on this tiny rowboat in the middle of the ocean. And the most likely, the obvious threat to your life is you're going to die of thirst, because that's going to be the limiting resource, because there's no fresh water on the boat. Now, medically, we know that if you take the obvious solution, which is to drink this, there's lots of water around you, it's just salty seawater. But of course, we know medically that if you drink the seawater, you're going to die even faster, because even though it will quench your thirst for a few seconds, it will actually pile up the salt even faster, and so you'll die even sooner. So the optimal strategy is to hold out as long as possible and not to drink the seawater, and hope that you find fresh water or are rescued. And that's actually better than drinking the seawater. Another strategy would be to come up with improvise a technology with whatever tools you have on the boat to try to separate the pure water salt, so that you can drink water that is not that is, you separate the salt from the water and drink the pure water, right? So that is actually what you want to do. That is actually, in some sense, the analogy to the long-term solution. So the quick solution is to drink the seawater, but that's the wrong solution. The longer, more technologically challenging solution is to separate the salt from the water and drink the unsalted water. Okay, so that's the analogy that I would draw. So that if you take, for example, some of my criticisms or observations of what happened in Northern Europe over the past decade, where they created huge tax breaks to make solar energy economically viable in, say, Germany. But as soon as those tax subsidies or tax breaks went away, the solar energy was no longer competitive. And if you look at the finer details of what actually happened during this solar boom in Germany, what would happen is solar energy is fundamentally intermittent. And so while the sun was shining, obviously they could produce enough electricity to drive their energy needs. But when the solar output was insufficient, but of course they wanted to still keep the economy going and they couldn't shut down the economy, what happened in Germany is they had to import electricity from Poland. And now you ask, well, how did Poland generate electricity that it could export to Germany? And the answer is, oh, well, they burned coal plants. So they had coal-fired electricity in Poland. So you were simply transferring the entropic effect, the disorder that would be created in Germany was transported to Poland. But of course, the Polish plants were even less efficient than the German plants. So in fact, you were actually worse off. And now that you're transmitting electricity over long distances between Poland and Germany, you were also going to lose a certain fraction of the electricity compared to if you had produced it locally in Germany. So I'm just using that as an example to show the analogy with the drinking the salt water example in the rowboat, okay? So now, the other thing you should think about, and again, if you go back to thermodynamics and ask yourself this whole question of life in general and human life, and especially having a very high quality of life, high standard of living, if you associate that with a very, very, and of course the sign, in the case of entropy, low order corresponds to life, high entropy or great disorder corresponds to non-living things. So if you create a huge minimum in entropy corresponding to a high standard of life, inevitably it's associated with creating a lot of disorder elsewhere, right? I mean, that's just thermodynamics. So if the government decides to make sustainable strategies optimum or effective in terms of driving human behavior, but the government decides to do that by creating huge tax incentives, in other words, using artificial economic incentives, you have to ask yourself, where did that money come from? And what activity was done to generate that wealth that is taxed to create the subsidy, okay? So in other words, if you create a huge tax incentive to drive a sustainable strategy, but then you follow the money and ask, how was that money generated? And if that money was generated with other non-sustainable activities, and again, given the inefficiency, again, using the transmission analogy of electricity, transmitting electricity from Poland to Germany, you're going to lose a fraction of that electricity compared to if you generated it directly in Germany. In the same way, transmitting the wealth from the group that produced the wealth through Washington, D.C., and we all acknowledge that our political system is not efficient, it's corrupt, it's got inefficiencies. So a certain amount of the wealth is lost in transmitting it from one part of the economy to the other. And then eventually some of that wealth finds itself to drive the so-called sustainable activity, okay? So all of these are artificial solutions that make you feel better. But if you apply sophomore chemical engineering materials and energy and entropy balance, you're going to be very unhappy with the conclusions that you come up with, okay? So the challenge for the young generation of chemical engineers is, because the point of my commentary is not that sustainability is wrong. The point is that it is a truly very, very difficult challenge with no easy solutions. All the easy solutions are in fact not solutions. And so the technical challenge of coming up with better materials, better systems, better designs, so that you actually deliver true solutions, that is the challenge that you will face over your career as a chemical engineer. So my generation, because I'm in my 60s now, we took the shortcut of using this enormous store of wealth in the depletable resources, okay? And we designed our systems based on the assumption that, to a first order approximation, that these resources would never run out. And through things like innovation in shale and so on, we were able to take these so-called depletable resources and get an extension for another 100 years, okay? So that clearly, given the extension of this energy paradigm by 100 years, it's gonna be lasting long past my lifetime. But the chemical engineers who are in school today, and if you think that your career is gonna be over a time span of, say, 50 years, then clearly toward the end of your career, you'll start to see the effect of the end of the bridging era, right? So the time when this enormous store of depletable entropic advantage, that end will be in sight as you approach the end of your career. And so clearly the economic activity and the rewards for your professional success will be set by what contribution you can make towards solving that problem, okay? Now, the penalty for not coming up with a true solution will actually be the collapse of civilization, right? So obviously, the world beyond humans will not simply cease to exist because we don't find solutions. The world will go on. It's just a question of what kind of world it'll be. So if we go with the false artificial solutions, which the energy, materials, and entropic balances tell us is not a true solution, but if we trick ourselves into believing they are the true solutions, then I am pretty confident 200-300 years from now, civilization as we know it will end, right? And we'll just go to if you follow the science fiction movies and the fantasy movies of a dystopic world, dystopia, where basically it's a world without civilization, and maybe humans don't even exist in the numbers we live in, numbers that we have today. So that is certainly one possible steady state in the future if we don't come up with a creative solution. There is, of course, an alternate, brighter vision where there are significant breakthroughs in material science and technology and systems engineering, and we come up with wonderful solutions. And so we have a sustainable society generating energy, efficient transfer of energy from the solar input into a high quality of life, right? Okay, so let me stop there because I've given you kind of a general framework for our discussion, and I'm happy to answer your questions.
Alrighty, awesome. So I'll start sharing some of the questions that we have in the chat. So our first question is, do you think the governments are prepared for developing sustainable projects? And do you think they are interested in that?
I think the short answer is government is dominated by people who have no training in the STEM disciplines. The biggest community, if you look at the backgrounds of the people who form our government, whether it's the executive branch or the legislature, and certainly the judiciary, the single biggest group are the lawyers, right? So, uh, so the very important in all this is the various engineering societies, including AICHE, the National Academy of Engineering, the National Academy of Sciences. There are various mechanisms by which insights from the STEM community are transferred to those who are elected representatives in a democracy, right? Now, in a country like China, where it's not a democracy, they can be lucky because for a number of years now, the top leadership in China has actually been chemical engineers. And you may or may not know that. Okay, so there they have a different government where many of the things that I talk about, their leaders already know because they actually have taken mass and energy balances and chemical engineering, thermodynamics as undergraduate students. Okay, but our leadership has not done that. So we end up giving these $500 million subsidies to companies like Solendra to build a solar energy plant, solar cell plant in Fremont, California. That was about 10 years ago. And their breakthrough design was their solar panels were going to be cylindrical instead of the standard one. Okay, that was absolute nonsense. And after blowing through almost $1 billion in government money, all of that money was created by non-sustainable, energy depleting activities to create that money, by the way, because much of our economy is not sustainable, right? So by definition, that money was generated with non-sustainable activity. And $1 billion of that was blown through with a really bad idea, right? So that's the government's track record. And what I'm saying is that if we continue on that path, and this is not criticizing one party or another, this is true of all government in a society that's not, the decision makers themselves do not have a STEM background. So the only way to break that cycle is for the next generation of chemical engineers like yourselves to be more actively engaged in conversations, either become, there are a few engineers who are elected to Congress and so on. So certainly you can see yourselves becoming engaged in the political process and directly sharing your insights, or become active in various organizations like AICHE to engage with the society, including their elected representatives, in giving the best possible STEM-centric advice on a truly sustainable strategies.
All righty, thank you for that answer. Much appreciated. So our next question is, to what extent do countries bear the cost of sustainable projects? Is the relatively low cost / output ratio of sustainability projects compared to other easy methods, is that enough for all the people in the world, considering the future as well?
So I think at the extreme, there are two answers. There is the ideal solution where everybody, all countries come together and say, okay, we need to solve this, and we all do our share and solve this problem. I think that's naive, and I think there's a realistic answer, and this is actually what's actually happening, which is the lesser developed nations with a lower standard of living, they feel, and to some extent, I can sense their historical perspective, that the wealthier nations have gotten to where they are by exploiting non-renewable resources, which was the shortcut. because it is the faster path, right? I mean, just do an engineering analysis, a sophomore chemical engineering, mass and energy and entropic balances. It's clearly the fastest path to a higher standard of living. So these much of the world that doesn't have that standard of living feel that they owe it to their people to take the shortcut. And it's up to the wealthier countries in like the United States and Europe and so on to bite the bullet and stop taking the shortcut and pay the price and share much of the and shoulder much of the cost of the more difficult solutions. And I think any global discussion will be along that framework. And since the wealthier nations are vastly outnumbered by the non-wealthy nations, okay? I mean, it's just the numbers, right? So if it purely becomes a democratic exercise in counting votes, you know which way the vote's going to go, right? So the majority of countries will say, we're going to take the shortcut because we have a long way to go still. And so, and that includes burning coal. And it's up to countries like the United States and Northern Europe and so on to figure out how to solve these problems. Of course, the reality then is from a technological challenge, it's an even bigger challenge now because if you talk about, for example, carbon sequestration, solving the carbon dioxide problem, you not only have to reduce or eliminate emissions from the developed wealthy nations, you have to now compensate for all the carbon dioxide that's going to be produced by these countries that are in catch-up mode, okay? And I think that's going to be the reality over the next 100 years. So that is the realistic answer. And so I think from a chemical engineering perspective, the solutions that you have to come up with are going to have to be even bigger breakthroughs.
Awesome. Alrighty, our next question is, what are some ways for us to create a balance between sustainability and affordability?
Okay, this might seem very biased because I'm in the research universe, and obviously you would expect somebody who's active in research to say the answer is more funding for research. But I want to give an example. Let's take solar energy. And I criticize previous investments and attempts of solar energy because they were doomed to fail, right? But that's not to say that solar energy doesn't have a future. If you look at the efficiency of solar cells, it's just an amazing, and in fact, there is a number of scientific discussions, even in places like YouTube, that is accessible to the general public. And certainly every chemical engineer should be familiar with these concepts. It turns out that historically, the theoretical or practical maximum in the efficiency of solar cells was thought to be in the 15 to 20% range. But if you look at the details of these silicon-based technologies, these are so-called single junction solar cells. It turns out if you have multi-junction solar cells, that historical theoretical limit does not apply. So now, with these multi-junction solar cells, you have solar cell efficiencies that are beyond 20%. And now there's talk of solar cells that have efficiencies in the 40 to 50% range. Okay, so that's an example of what you get from research. So again, going back to the analogy of the person stranded in the rowboat, it's not to say that you shouldn't drink the seawater because it's going to kill you. The right solution is come up with the right tool to separate the salt from the water and then drink the purified water, right? So in the same way, I'm not saying that solar energy is doomed because it's inefficient. The right answer is come up with better materials to increase the efficiency of the solar cells from the historical numbers. In the early days of solar panels, they were as low as 5, 6, 7%. Now imagine a world where the solar cells are mass produced in large quantities with 50% efficiencies. That's a game changer, right? At those types of numbers, and in a world where fossil fuels are almost depleted, that's an example. Another example is come up with the right systems, engineering, and the safeguards to make nuclear energy safe. And nuclear energy is an example of a highly concentrated form of energy where even if something goes wrong, the damage can be localized and contained. Okay, so a world based on highly efficient solar cells and very, very ultra safe nuclear technology, that's the type of future that that can generate a high quality of life for the numbers of people that we have on the planet right now. So I see that as a pathway to what a great society could look like 200 years from now.
All righty, great answer. Thank you for that. We have a next question. What do you think about the future of chemical engineering? Can technology or AI replace the chemical engineers in industry? And are we sustainable going forward?
So, of course, again, I'm going to be very biased. I'm going to show my bias as a chemical engineer. I believe chemical engineering is the single best major on the college campus today. And I'm sorry that a number of universities don't have a Chem-E program. But if you're fortunate enough, as you all are, to be at a university that has a Chem-E program, lucky for you. The other thing that you're all very lucky is that chemical engineering goes through these cycles of roughly 10 years in duration, from being very popular as a destination for high school students to becoming very unpopular. And so I know in much of the Chem-E programs today, we're at a low point in that cycle where the chemical engineering enrollment is maybe down to about 50% of what it was at a peak of, say, 4 or 5 years ago. And this is actually a normal cycle. And right now in high school, a lot of the guidance counselors and the teachers and the parents are telling their children, don't go into chemical engineering. Look at all the problems in the energy sector. Companies like ExxonMobil are laying off people and so on. So chemical engineering is not a good major. You should all learn Python and coding and go into computer science and so on. And so what's going to happen is, and especially for those of you who are sophomores, in about 2 years when you are graduating with a degree in chemical engineering, there will be a severe mismatch between the societal demand, industrial demand for chemical engineers, and the number of chemical engineers produced by the universities. And so every graduate will get 4 or 5 job offers, okay? Because there literally will not be enough chemical engineers to fill all the demand. And the reason why I feel confident saying this is I remember back in 2004, and I remember this like it was yesterday because I was actually in Washington, D.C. working for the National Science Foundation. And a survey had just come out that showed that chemical engineering was the worst possible and least popular major in the STEM disciplines. And that the number one choice back in 2004 was computer science because everything was IT. And what happened in the next 4 or 5 years is exactly what I'm saying today, is that there was a boom in the demand for chemical engineers. And there were so many people coming out with computer science degrees. And at the same time, companies decided to outsource their IT to India. So all these people who went into computer science couldn't find jobs because there were no jobs in the US in IT. Meanwhile, every student who came out in chemical engineering was getting like 4 or 5 job offers because there was essentially no competition and everybody wanted chemical engineers. Okay. And chemical engineering actually is always small numbers to begin with because first of all, if you don't like chemistry in high school, you're not going to pick chemical engineering, right? And so because chemical engineering requires so many different things, chemistry, math, physics, the number of people who actually come into chemical engineering is already small to begin with. And then when that supply is further reduced by 50% by societal perception, then the number of graduates coming out at the other end at the low point of this 10-year cycle is really going to be very small. Now, the reason why I feel very confident, going back to the theme of my discussion about the quality of life ultimately being about optimizing entropy, right? So you're localizing the low points of entropy. And that's what chemical engineers can do. That's what chemical engineering teaches you how to do. So whenever we have normal economic cycles, and especially during good economic cycles, companies will want to hire people who can figure out how to solve those challenges. So whether it's disguised as creating a better process to save on energy costs, or create a better process to lower environmental impact or environmental damage, or meet tougher environmental standards, all of that are chemical engineering challenges, right? They're not going to be, there's not enough known about the principles of these so that you can simply design that with purely a computer science degree. So companies like Dow Chemical and others have hired people with computer science and mathematics and statistics background who are world-class experts in AI and machine learning and so on. And what they find is that that by itself is not enough. And they try to teach them chemical engineering so they can use AI more effectively in their companies. And what they discover is that by the time you are in your 30s, even if you're an expert in mathematics or AI or statistics and machine learning and so on, it's very hard to teach somebody that old the fundamentals of chemical engineering, because chemical engineering is a very difficult discipline to learn. You have to learn it when you're young, just like mathematics. And so what these companies are now doing is they're discovering that it's easier to teach a chemical engineer who already has a strong math and science background. It's easier to teach them some machine learning and computational methods so they can talk to the AI experts than it is to try to teach an AI expert some chemical engineering so they can talk to chemical engineers. And so I think the answer to your question is that instead of chemical engineering being replaced by AI, what's going to happen, and actually Purdue Chemical Engineering was one of the first. My own background, by the way, is machine learning. That's what I've been doing since the late 1990s. So I've been doing this now 20 years. Long before it became popular. And in my executive role in the pharmaceutical industry for Eli Lilly as a vice president at Eli Lilly and also at a company called Park Davis Pharmaceuticals in Ann Arbor, Michigan, I was the head of research IT and research informatics. So that was the part of the pharmaceutical industry that I was involved in. From 1997 to 2003. So I've been doing this longer than most chemical engineers. And so Purdue Chemical Engineering was one of the first to create a undergraduate elective, a senior elective, and also a graduate course for machine learning and data science. And it's going to be offered again this coming spring semester. And so I know many of our undergraduates have the option of taking that in their senior year. So I think, and even though it's an elective right now, it's probably going to find itself into our 300 level course, which is our statistics course. So I see the standard statistics course that most chemical engineers take, typically in their junior year, that will evolve over the next 10 years, or even on a competitive pressure, it may evolve even faster over the next 5 years to include more and more data science elements into that course. So it'll be basically statistics and data science is how that course will evolve. And so I think the chemical engineers that are coming out today and in the future will have no difficulty in collaborating and talking with the AI experts. And that will make them among the most valuable employees in all these high-tech companies, as well as the current industries that hire chemical engineers, including the food companies, the energy companies, the consumer product companies. But I also see the big software companies of the future hiring chemical engineers as well because of the sector applications.
All righty. Our next question is, which is the best renewable energy sources that has the most potential to provide the energy that is demanded from humanity?
So the first answer, in my opinion, because of, again, energy density and the huge volume of energy. So again, I would encourage every chemical engineer to make this calculation. Look at the number of cars that we have. And by cars, I don't mean just personal vehicles. I also include the trucking fleet. Every time you decide to do online shopping, somebody has to deliver that package to you. And that package comes to you in a truck, right? So if you drive on the interstate, you see these big Amazon Prime trucks delivering your packages, right? So you must include all those in your calculations. So imagine that we decide that every one of those vehicles is going to be driven by an electric car, not hybrid, because we're going to go completely away from fossil fuels, okay? So it's all going to be 100% electric. And you should ask yourself, how much electricity does that correspond to? And compare that with the current generator capacity for electricity. And it's also an interesting exercise because we don't have a uniform distribution of population. We have parts of the country like coastal California, which has a very, very high concentration of cars. So you should ask yourself, if everyone in Southern and Northern California, so basically I mean from San Diego all the way up to the Bay Area, if every one of those people wants to use electric cars for their personal travel and also for their deliveries, how much electricity does that correspond to? And let's also, just to make this more interesting, let's also assume, because they're in California and they're politically correct, they don't want any more power plants built in their neighborhoods, okay? Because they're going to be politically driven. We know their politics, not in my backyard. So all that electricity is going to be generated in Arizona and Nevada and transmitted over power lines from Nevada and Arizona. That means you not only have to figure out how many more power plants Arizona and Nevada have to build, you also have to calculate how many more high power transmission lines have to be strung up between Arizona and Nevada on the one hand and coastal California on the other, okay? And you can also take away half of the power lines that are currently in place because they're old infrastructure, and every time there's threat of brush fires, those transmission lines have to be shut down. So you probably know in the news that there are seasonal brownouts and shutdowns of electricity generation, so-called rolling blackouts, even with the small percentage of the fleet that's currently electric. There's already blackouts in coastal California in the Bay Area because the current transmission capabilities between out of California into the Bay Area is insufficient. And whenever you have threats of fire conditions, the strong winds, and because of the significant threat of fires that go out of control, they have to shut down power transmission. So those lines are useless, okay? So you have to come up with new and better infrastructure that doesn't get shut down, because obviously if the entire vehicle fleet is electric, you cannot have a rolling blackout, right? I mean, that society would just go into chaos. You would literally have people starving to death if you did that. So you have to come out with transmission lines that are not shut down. So you should figure out how much more generating capacity that you need and how much more transmission lines you would have to build. And this is not a difficult calculation. This is a standard homework problem in your sophomore chemical engineering energy materials balance class. And so the answer to that question is obviously not a very pleasant answer. And so if you think of that just in the context of one area, but now think of it as all of the United States. So clearly you need what I call a robust strategy. You cannot put all your eggs in one basket and expect an energy system that is so efficient that no matter where the energy is produced, you can magically transfer it to wherever it's needed, right? So you need to have a combination of the most efficient renewable energy, so these future of multi-junction photovoltaic cells and so on. You also need to have a huge investment in energy storage technologies, much beyond anything we have today. And you also need technologies not like nuclear that are going to be operating 24/7 to provide reliable energy, even when the sun's not shining, and even when the battery systems are, energy storage systems have to be shut down or repaired or going off cycle. So in other words, there's going to have to be a very robust strategy that will deliver energy at all times whenever it's needed. And so you're going to have a base load, you're going to have intermittent loads, peaks and valleys and so on. So there's going to be, and there are chemical engineers who are in the area of process systems engineering. So this is those professors who teach your capstone design course as well as your process control course. So in the research side, those professors are designing the energy storage systems of the future for baseline loads that are generated with nuclear energy, and then variable loads that are met with highly efficient storage systems and renewable energy sources like wind and solar.